Micro is a subject that one needs to go over again and study to understand the basic concept. In our last class, we discussed uh, consumer's choice. Do you remember? So we are studying how consumers make choices when they encounter uh, when they encounter different preferences. So how they make their choices. So in that regard, we we look at some terms which includes the commodity. All right. So it's just a set of preferences. So commodities. So we also look at the consumer sets. The consumer sets are mainly affected by some physical constraints. So in this graph, we look at some physical constraints are visible to our consumers when they make their choices. So for instance, when one need to uh, check for there's a time constraint. So in the consumption of bread. So in the production of bread, so the time constraint is 24 hours. So also we look at consumption of setting of bread in New York and consumer of bread in Washington. And we also said that it's not possible or it's not feasible to consume this bread at this time at different location. So of convex sets and a concave set. All right. So when designations of items that are outside the set, for example of a concave set, just like this is an example of a convex set, including this. So these are the things we look at in the last class. So also we also had we also had some instances where we want to look at some problems or some constraints generally in real life activities. Some of the constraints that affect consumer choice include price and worth. So we said when two physical things that affect human decisions or when trying to make choices. All right. So we said the prices. So these are just set of vectors. Okay. So a set of vector, a one-dimensional vector by n. Also, we have your x1, x2 is your x. That's your consumer consumption set. All right. So if we have subscript there, they are unit prices. Right. This one with subscript one, subscript two, they are unit uh, commodity set. All right. So the one without subscript here is just your vector. I think that is clear. All right. So these are some things we look at in the last class. So in this class, we are going to look at demand functions and comparative statics. All right. So demand function is just a mathematical relationship between two moguls. So like I said, demand function, we are looking at it as a function. Function is any replicate or that we can derive a lot of smaller units from. So it's just a bigger set, all right? So that's like a function that can generate other outcomes. Yeah, so that's function. If you look at from the Wallacean demand here, so we have P of X is equals to W. This is an hyperplane function, all right? So this is a function, all right? So And by the time I make X separate formula, then I will have X is equals to what? W over P, right? So that means X is a function of what? W and P. So by the time I get a value for W and I also get a value for P, I will know the value for X. In the last for bread cost 1,000 naira, then the price is, let's say, 500 naira. When I use 1,000 to divide 500, I'll have 2, right? So that means 2 units of bread. So that is my hex. So whenever I know the value for weight and price, I'll be able to determine hex. So x is a function of weight and price. So that is how we show the relationship. All right. So generally, we we call such function a demand function. All right. Any question? All right. So we call that function a demand function. On the other hand, comparative statics is just is when we try to perform to determine how this price or wealth affects the equilibrium prices or the equilibrium of our model. So in that context, what you are looking at is comparative static. It's just an analysis about the equilibrium points of a certain commodity. All right. So we want to look at the general equilibrium or a partial equilibrium or just a static equilibrium for a particular price and weight. So in that concept, what we are doing is comparative study. We are providing an in-depth analysis to prices and weight, or how prices and weight uh, affect the demand of a particular commodity. So in that regard, what we are looking at is a comparative static, all right? So, and we said all of this, and when we are trying to look at equilibrium, we must look at the budget line. We look at them around the budget line. So in last class, we discussed what the budget line means, right? So we said budget line. Well, I think I gave us the question of a budget line, if you can recall. So let me recap again. So this is an equation of a budget line. So, all right, P of X is equals to W, or P of X is less than W. So X equals W. So when you have this equation, this is just like equation of a budget line. It can be summation of so many what, so many commodity, all right? And we also show that this is the budget line, all right? So we also show that this budget line can be negative most time. In fact, it's always negative, all right? Whenever X, the commodity, all right, is not negative. And we always have this negative slope, P1 over P2. These are the negative slope. What does that mean? So the slope actually inform us the rate at which a particular commodity is being consumed compared to the other. So it means that as one commodity is increasing, the other commodity is what is decreasing. All right. So both commodity cannot increase simultaneously. That is what the economics slope is saying. So as P2, P1, maybe P1 is increasing, P2 is decreasing. That's commodity one is increasing, commodity two is also decreasing. So that is what that concept is saying. So I think we look at some equations of how to derive this. We can also look at how to derive this, some of the slope, the intercept of our budget line. You can just play around with those mathematics concepts. All right. So let me share my other screen. Is this screen visible? Can you see my screen, please? Can you see anyone there?
Hello?
Yeah, can you see my screen?
Yeah, I can see it.
All right. So we want to look at some budget line. So yeah, before then, I have some questions we need to quickly look at. All right. So here I just want to talk about the budget line. All right. So say this is the budget line. So by the time to get our, this is the slope. All right. We know what the slope means. The change in price, that's a slope. Then for me to get my intercept, I need to substitute 0 in place of x1 to that to get my vertical intercept along the y-axis. All right. So along the y-axis, when I put uh, x to be 0, I will have x2. Making x substitute of formula, I will have this expression m over p. So that is my vertical intercept. To get my horizontal intercept, all I need to do is to put uh, x2 to be 0. All right, then I will have my vertical intercept. All right, so these are the slope. So, um, like I said earlier, the intercept is always positive, or it's always negative. All right, it represents the rate at which what a consumer a consumer trade a particular goods, while the other one is kept constant, or the other one is decreasing. So one is increasing, the other one is decreasing. So that is what that is saying. So I think I have question for us to solve. So that is just some little things about comparative static, all right? So now we can also look at some definition that uh, associates with this comparative static, all right? So like uh, like we said in the last class that the consumer various demand or correspondence. So it's how these prices affect each others. All right. So, but one of the findings or one of the implications of this is that naturally there are some goods that are homogeneous. That means when this price or weight the changes. So some of these change between this function, price and weight. So sometimes could be homogeneous. What does that mean? Homogeneous is saying that uh, the consumption of a particular goods, all right. So as price increases or the weight also increases, sometimes we can have uh, we can have our the consumer not making change in his decisions. All right. So that what we mean by homogeneous. Sometimes consumers are on change whenever or the choices of consumer remain unchanged whenever prices or weight are being affected. All right. So that's what homogeneity is saying. So homogeneity of degree 0 so says that what the demand function or the demand function of a certain or the demand behavior of a certain consumer remain unchanged, whether price or weight is being scaled to any particular figure. All right. So even though the price and weight are double or are tripled, some consumers are not affected by such in their choices. All right. So that's what homogeneous is. I don't know if you understand that clearly. So I have some a little exercise here. So it says if a consumer, okay, this one is still on budget set, said that if the originally a consumer is faced with this budget line, remember, so this is our equation of the budget line for two commodity, all right? So two prices, two commodities, M is representing the weight, all right? Some textbooks represent it with M, while some textbooks represent it with W, the weight, all right? So he said then, if goods one is doubled and the price of goods two is 8 times larger, all right, and the net income become 4 times. So what will be the equation? Can anyone tell us? We have this question. So this price, the first price is doubled, the second price is 8 times the original price, while the worth is 4 times the original worth. Then what could that be? What would be our equation for the budget line? Anybody? So in that regard, when the price of goods one is doubled, all right, we understand that uh, P1 will change to 2. So we'll be having 2x1 here, all right? Why in this place we'll be having 8x2, and in the other end here, we have 4 times m, all right? So that will be the new equation of the line. So now we can also graphically illustrate this. So the next question is that what happens to the line, all right, if goose 2 is increased, but goose 1 remain, the goose 1 remain unchanged, and also the income remain constant. So what will happen to that graph? Anybody? When you plot a graph for this, or for this budget, yeah, for this budget. So what will that looks like? Anybody? Mr. Jackson? Chidazi, are you there? Chidazi, are you there? What will happen to our graph or the budget line if goods 2 is increased and goods 1 remain unchanged? What will happen? So the answer to that is this. You remember after you've drawn it, all right? So when you increase goods 2 on the x-axis, what will happen to the slope is that the slope will be what? Will fall and to become uh, it become flattened, all right? To become flattened, going parallel along the x-axis, all right? That will happen. So we said the answer to this is that the slope will what will remain flattened or will become flattened, all right? So why this one is why goose one is kept constant, so the slope becomes sloping. Then in goose two, what will happen to goose two is that if goose two is decreased, all right, the slope will become slippery. So you understand, become more slippery, moving closer to the y-axis. So you have a very sharp slope moving towards the y-axis, all right, if it is decreased, all right. So and he said if the price of goods one is doubled, all right, and price of goods two is tripled, then the budget line become what? So you're asking, does the budget line becomes flatter or steeper? So in this regard, so remember it goes up, so it becomes flatter because goods one is doubled, is moving up, so both of them are increasing. All right, so you have a more flattened slope. So now to the other question, okay, we have a preposition or a proposition from the definition from homogeneity of demand correspondence. So this aspect is saying that what if you have a demand correspondence that is homogeneous of degree zero, then what will happen uh, is saying that a multiple of price, alpha represents multiple, is a constant what number. So it says that a multiple of the price and a multiple of the weight can still remain the same, does not change. All right, so there's a proof for that. I will give us a proof. Let me give us the proof now. So when you multiply your prices by a lot of value that is not zero, alpha is greater than zero. So I also multiply your weight by the same thing. Definitely it's still the same as long as their degree is zero. What do we mean by homogeneous of degree zero? It means this alpha should have a power to zero, all right? So if alpha is to the power of zero, remember a concept in mathematics that says anything to the power of zero is what? Is one, all right? So you just become alpha to the power of one, then here alpha to the power of 1, then you're going to have your function back. So that is, so let's provide a proof to that. So yeah, let me provide a proof to that. So the he said the demand function is set to satisfy homogeneity of degree zero if for any positive constant. So I'm using lambda to represent alpha, all right, in that proof. So instead of using alpha, I'm using lambda. They are all constant, all right. But then these functions remain the same, all right. To see this proof, to see this proof, yeah, suppose this is constant, then we consider uh, our alpha. So let's consider the right hand side of this, all right? So let's show that we can have a left hand side. So all we just need to do is to bring out this, since it's a function, it's a linear function, all right? So we can bring out our lambda outside of the bracket. So this is a correspondence. So remember that uh, your P1 and your X1. So if I have a lambda outside this, I can just shift it outside the bracket. So with that knowledge now, so they are, so we can shift this lambda out of this bracket. So you have to do it logically, okay? So, and then, so by so doing, okay, so we can, okay, I'm just writing this statement in this form. So we have our x of lambda, which is the left-hand side. So I'm assuming that is in this form. Then, since this is a constant, we can move it, we can factor it outside the bracket. All right, so when we factor out that, we'll have an expression that looks like this. So we have an expression that looks like this. So you can see, so you don't bring it out of the x directly, to bring it out of p and w. All right, then the next is to bring it out of x. So you can see. So by breaking it out, we can assume that this guy is of this form. So whenever our lambda is to the power of 0, all right, so it's of degree 0. Put lambda to be 0, that is the power of lambda is 0, then it becomes what? 1. So, and we have that function back. So that is the simple proof to that, to that, to that expression, all right? So that is the simple proof. And let's go to the other side. So there's still another, okay, we have a question here, all right? So before we see the next implication of the correspondence, of the demand correspondence. So here is a question to support what we've just solved. That suppose that we have our L to be 3. When L is 3, you know what that means, right? So we're talking about 3 commodity are present, all right? So if we have 3 commodities are present, L1, L2, L3, so which can be X1, X2, X3, all right? So we are asked to show that if uh, if this function x of p of w satisfy homogeneity of degree 0, and if okay, and when the Wallace law, if it satisfied the Wallace law, when, sorry, this is beta, all right? So this is beta. There's an error here. This is beta. Then beta is equals to 1 when beta is between 0 and 1, all right? So correction quickly. Um, yeah, I've made the correction. So when beta is equals to 0 and when beta is within 0 and 1, all right? So then, sorry, let me do one more correction question. So one more correction says that, yeah, All right, so this is the complete question. All right, so yeah, so from this now, so we have to show that when beta is equals to 1, so and when beta is found between 0 and 1, like I defined what the set means in the last class, right? So I said that you have a coily braces like this, or yeah, this type of braces, all right? So it means an open set. So 0 and 1 is not inclusive. If I'm having a square braces here, it's a closed set, all right? 0 and 1 are inclusive, all right? So I hope we are following.
Yes, we are following. I'm following.
All right, thank you very much, sir. Please, if you have questions, you can signify and or drop it in the chat box. So now we are given X1. Remember, X1 is is a commodity that is a function of price and words. All right, X2 is also a commodity. Remember, the question told us that we have a commodity set of three. All right, so that is why we are able to define three correspondence. So this X3 is a demand correspondence. So this is a function that is associated with it. All right, so this is beta P1 and W. All right, so now let's check if these three questions or these three functions are homogeneous. We are going to do each of them differently. All right. So you do for the first one, you do for the second one, you do for the third one. So you check homogeneity. What are we checking here? Whenever I increase my P by any alpha, all right, or by lambda, or whichever one that you're convenient with, whenever I increase it, all right, will where the right hand side gives me the left hand side. That is what we are trying to say here. So let me stop sharing and share my second screen. So to do that, let's first of all define our questions. All right. So let's define our functions. So these are the functions that we are given. All right. So first we substitute lambda into x1. So when you do that, so anywhere you see p, replace it by what? By lambda p. All right. So anywhere you see w, replace it by lambda w. So also we have p at the denominator. All right. So everything becomes lambda p. Then by the time you factorize, so you discover that all p can go to can come outside the bracket, just like from the proof we saw earlier. We we factorize out all lambdas. All right. So we can factorize out all lambdas here. So and when you do that, to factorize out all lambdas, you have P2W left at the numerator. So they will cancel out because they have degree zeros. All right, so this is the power of 0 becomes 1. So when you factorize out all P here, so it becomes P1 plus P2 plus P3. So everything, all P to the power of 0, so it becomes 1. All right, so, and this is originally the question that was given to us. So, which is still what we have here. Also, similarly, you do the same thing for x2. So, by substituting lambda into the function, all right? So, if you're having this lambda here, you have this lambda here. Also, you do that to the denominator. So, by the time you factorize out all this lambda, you're going to have lambda. So, this becomes lambda to the power of 0. Also, in the denominator, you have lambda to the power of zeros, then they cancels out. You have your original question back. I don't know if this is clear. Is that clear?
I'm not too clear with your last explanation.
All right. So let me
Yeah,
re-explain.
you talk of lambda to the power of zero or something and
Yes.
cancel out.
Yes.
Sorry, there was this writing pad that Chisom used on Good Friday. I
Yeah.
don't know. As if Friday.
Yeah. On
Why don't
Friday.
you use the same? It was Friday, right? Why don't
Yeah.
you use the same kind of pad for this class? I think it will help better.
What about this?
Okay, let me look at it.
Yeah, I'm using software to write though. So uh is the writing pad prefer?
I don't know the way she was doing it. I see it was on the board somehow.
Yeah.
Okay, no problem. You can continue with this. Let me
All
know.
right.
I can continue with it here.
Yeah. So let me factorize out all lambdas. All right. So when I factorize out all lambdas here, I'll be having lambdas to the power of zero here. Let me include that lambda to the power of zero so you can see what I meant by that. Yeah, just like we rightly have it here. So you can see that we factorize out all lambdas here. So this is the lambdas we are having. Also in the denominator, we have lambda here, we have lambda here, lambda here. So we factorize out all the lambdas. All right, lambda cancel out lambda. All right, we'll be left with an expression that looks like the original expression. All right, so that is exactly what I'm saying. So, and that is nothing but x2. All right, I don't know if that's clear.
It's clear
So,
now.
so when you're checking for homogeneity, all you just need to do is just to replace it with a certain constant. All right, check if whenever you can factorize out the entire lambda, check if you're going to have your original question back. So if you can achieve that, definitely question to satisfy homogeneity. All right. So exactly after casting out this, so you can see that this is what we have, and it's the same thing as the question back. All right. So that is that. Then let's look at the third one. Will you be able to attempt the third one?
Sorry, I was distracted. Sorry. What did you say?
Will you be able to attend the third one?
Which is the third one?
You know, I've done for two. Let me show you the
Yes.
third one. Let me show you the
Okay.
third one. So here is the third one. Yeah, this is the third one. I've done for these two. X1, I've done for X2. All right, the third one. Will you be able to attempt it?
I'm still looking at it. As this equals to this.
So your next approach or your next step is to create a lambda here. All right. So
Yes,
substitute
yes,
lambda p, lambda w. All right. So when you
yeah,
have lambda p, lambda w, so when you have lambda p, lambda w, so remember lambda beta is just a constant. All right. And we are told in the
yeah,
question that beta is 1. So
yeah,
substitute beta to be 1. All right. Then
yeah.
here you have WP1 here, lambda P1, you have lambda W. In the denominator, you have lambda P1, lambda P2, lambda P3.
Lambda P3, P3.
Yeah, so you can factorize out lambda completely here, right? The same
Yes.
thing in the numerator. So when you do that, they will cancel out. You have your original question back. Is that not? So
Yeah.
that is how to show the homogeneity. So let me show you what I have in my later. So that is the exact solution. Is it visible? So that's the exact solution I have here. So you have substitute lambda into it, then the lambdas cancels out, then you have your x3 back, all right? So that is that. So for the other question we have here, so for the other question, see, I have a second question here, which says if we have a Cos-Douglas equation. So this is a Cos-Douglas utility function, all right? So in this is another question. So in this Cobb-Douglas utility question, all right? So it was subjected to this budget line. You can see this is the budget line. So this function was subjected to this budget line, and we have an outcome that looks like this. So we're asked to check if these functions are homogeneous. All right. So let us look it together. So for the first one, what are we going to do? We substitute lambda into W, right? So we substitute lambda into P2. Then we're going to have W, lambda W here. Also, we in the denominator, you substitute lambda P1, you have lambda P2, right? So you discover that lambda P1, lambda the numerator, we cancel out lambda in the denominator. So and that function is what? Homogeneous, all right? So if you
Yeah.
also look, yeah, so if you also look at the second one, I think that one too is homogeneous. So look at it very well. So it's also homogeneous of degree.
It's also homogeneous because it's almost the same like the first.
Yes. So that is how it looks like. So that's how to check for homogeneity. So I can give us some questions and ask us to check if it's homogeneous or not. All right. So that is just the procedure.
Okay.
So
Okay.
now it can be homogeneous of degree 1, it can be homogeneous of degree 2. So you depends on the question. So by the time you substitute lambda into it, whatsoever you have, some could be of degree 2. Maybe the next class I'll get a question of degree 2 or of degree 1. So if the lambda does not cancel out completely, you have just maybe one lambda left is of degree 1. So if you have maybe lambda to the power of 2, all right, let's say this is x to the power, instead of x alpha is x to the power of 2. By the time you substitute lambda into this, then you have lambda square, for instance. So when if that is the end of the solution, it means of degree 2, all right. But in this case that we've solved, they are all of degree zeros, all right. So now we said when we are looking at comparative static or the analysis, how this uh, how this constraint affects our demand correspondence, all right, or the choice of demand we are making. So well, we usually run to what we call two effects or two of the comparative static. So they are the most common ones are the weight effect and the price effect, all right. So weight effect is just like uh, the change in weight in a particular goods. So the change in weight for a particular goods. So that is what we are looking at here. So, and that function, the weight effect, sometimes it is sometimes called the angel function, and this is a derivative for it. So it means when you change in x in your commodity, when the change in commodity depends on the weight you are having. All right, for a consumer to make a particular choice of a for a goods, so the amount he's having will depends on what the number of goods he can purchase. That is what the weight effect, something like that. So that's what the weight effect is saying. So, and in that regard, we'll have our weight effects to be like a matrix, all right? So it's just like a matrix. So this matrix will be a one by one matrix. That means x1, x2, x3, so weight 1. So you don't have numerous weights, so your weights remain the same for different goods you want to purchase. All right. So if you're having a set of goods that is of x1, x2, x3, your weight relatively remain the same in making choices for all of these commodities. All right, so that's what the weight effect is saying. So the price effect is a set of L by 1 matrix, all right? So, or L by N matrix. So what does that mean? It means that we have multiple uh, prices for the same particular goods. Yeah. So depends on location and depends on time or season. All right. So that makes our weight changes at our price changes for a particular goods. Say goods one is being sold at maybe 1,000 naira in, let's say in Abuja. Then when you go to Kano, you have it at another price. When you go to Castina, you have it at another price. When you go to outside the country, you have it at other prices. So this is what is saying that at different locations or at different situations, a particular goods or a particular commodity would have different prices. So it could be maybe change, it could be as a result of scarcity, it could be a result of monopoly, it could be as a result of tax, all right? So these are what we affect prices. So we know how that works in our society. So what you get in the market today, that's not the price you get it tomorrow. So that is what he's saying, that at particular location or particular time or at some certain instances, the price for a particular commodity may change. So that is what that aspect is saying. And also we'll have we're going to have uh, what's it called? We can have uh, some some intuition from this effect. So from the homogeneity, all right. So when we're having homogeneity of a good, some of the consequences. So that is what we listed in our preposition here. We say that if your answer demand function is homogeneous of degree 0, then for all p or for all weights that we can pick, all right, then you have a question?
No, no question, please. Continue.
All right. So for all prices that we can have, definitely we'll have, we'll, okay. So for all prices, then we're going to have all of these instances. That means change in words. So change in commodity. So this is like calculus, all right? So this coily D here is means partial derivative, all right? So partial derivative of the goods to the partial derivative of the price, all right? So also partial derivative to the of a particular goes to its weight. When you sum them together, it's always zero. So this is just more like elasticity. So this just represents elasticity of price, elasticity of weight, all right? So it's saying that elasticity of price and weight will result to what? Will definitely give us zero. So that is what this preposition is saying. There are proofs for it, all right? So I will provide the proofs. Also, we, yeah. So let me look at the, let me show us the proof in a few minutes. So similarly, we also have similar preposition also. Yeah. Okay, this is the preposition that also follows that if the weights or the Warshak demand function satisfy a Wallace law, all right? So we know what the Wallace law says that, right? The Wallace law says that the product of price and commodities, certain commodities equals to a weight. So it is saying that whenever we have that, we can also have a matrix that looks like this. This is the weight effect. That the weight effect is equals to one. It is constant. It remains unchanged or true. That's what this preposition is saying. So let me quickly provide the proof to some of this. So here are some of the proofs. Um, so let's understand the concept of derivatives. All right. So in order to understand this, you must go and check calculus back. Understand what the calculus is saying. So let's assume, yeah. So yeah. So let's say we remember this function, right? Do you remember this function? This function is our demand, our Warasha demand, just like P times X, all right? P times X is equal to W. I'm putting this summation there because I'm having many prices, all right? P1, is taken from K is equals to 1 to L. So I can have P1 X1 is equals to W plus P2 X2 is equals to W. Understand? So that is what this is saying. So this is the Warasha uh, this is the actual constraint, budget constraint equation, all right, that I showed earlier. So from this constraint equation, I differentiate both sides, all right? So when I differentiate both sides, all right, with respect to what? With respect to P. P is our price. So when we do this derivative, so then we have to apply the product rule of differentiation. So product rule of differentiation is saying that hold a particular variable constant and differentiate the other, then hold, then sum it with the other one constant, the derivative of the other one constant. So what does this mean? So in this case now, we hold p constant and differentiate x with respect to p. All right. So when I differentiate x with respect to p, this is what I have. All right, while holding p constant. Then when I hold x, this function x p of w constant, I differentiate p with respect to p. That will give me 1. All right, so when you differentiate a constant or a value with respect to itself, it is 1. So that is how we have this, and is equals to what? 0. Then what I'm going to do next is to apply the rules, or to apply the summation rule to this equation. All right, so when I apply it, then I have my formula. So let me apply the summation rule to it. So when I apply the summation rule to this, all right, okay, we multiply both sides by weights. Remember, we are looking for the elasticity. Yeah, so multiply both sides by weights, then we have this equation. Then the next thing is to apply the summation rule, which takes from goes 1 to L to it. Then we have the summation uh, of partial x with respect to t plus summation of partial p with respect plus summation of the product. Everything together, we have our 0. So we can now divide both sides by w, or we've almost come to the end of that proof. Do that. So by the time you apply the sum rule to each of these formulae, all right, so then we have this final value. So that is the solution to that. So if you watch the video very well, maybe you understand. So I don't know if you get it clearly right now. Do you?
Yeah, I'm full.
Come again.
I say I'm following you. I'm
All right,
following
all
you.
right, all right. Thank you very much. So this you must go back and check your calculus very well. All right. So now we can also have a situation. Yeah. So we can also have a situation, another implication of another application from that theory. Let me bring down the screen. So we can have another application to this theory. So yeah, yeah. So like I said earlier, from this we can restate it in a matrix form. So this equation is just the matrix form, all right, of this equation. Here is the summation form. This is the metric form. So in this matrix, into a metric form that looks like this. This is a metric form for this price. You can see that this is this equation that I converted to a matrix form in this order. So also from this form, you can also convert it to a matrix form that looks like this. All right. This is just P. This is the P. Then this is summation of all of this. Then each of these P, they are vectors, all right? You can see all these ones have subscripts. So these ones are not with subscripts, so they are summation, all right? So also, yeah. So if we look at all of this very well, each of these, they represent elasticity, all right? So each of these is just elasticity of price. This is also elasticity of weight, all right? So the elasticity of price and weight, these are, so I just brought out the derivative because we are going to make use of this formula as we proceed later. So to make some provings, all right? So that is what we have there. Then the other preposition from this demand function, we can also have a proposition or a derivative from it that says that if we have if the Wanchia demand function satisfy the Wallace law, then for all prices and weights, we can have this equation, all right? So this equation is similar to what we just proved earlier. So you can verify the proof at your convenient time. So you're going to have this is equals to 0. So we don't have weight effect here, right? So we only have price effects. So price effect and your commodity is equals to 0. So it's still based on the knowledge of calculus. So if you use calculus to prove it, you have this outcome. So you can prove that. So we also have this that says if the Wallace demand function satisfies the Wallace law, then for all P and W that we can uh, then for all P and W that we can have access to, we can have this formula also existing. So it's also based on calculus, all right? So let me quickly share my screen on the proof. So you have that one to prove. Let me prove this for you. Yeah. So here is the proof for this. So to prove this equation that the weight effect and price is equal to 1. All right. So to prove this equation now, so all we just need to do, multiply through by what? W. Any question? All right. So all we just need to do is we restate the equation, the budget constraint equation. So this is the budget constraint equation. That's Wallace law. All right. So the Wallace law, which says that the price and weight, the product of price and the commodity is equal to a vector space P. All right. So then all we just need to do is to what differentiate this equation. So by the time we differentiate this with respect to weight. Remember in the first equation, in this equation, we differentiate with respect to price. So in this equation now, we are differentiating with respect to weight, all right? So partial derivative of the weight and partial derivative of this equation with respect to the weight. So when you differentiate this equation with respect to weight, you're going to have 1. So when you differentiate this equation with respect to weight, then we are going to apply our product rule of differentiation again. You understand? So you hold your P constant, you differentiate X partially with respect to weight, then you sum it to differentiation of X partially with respect to P. All right. So then you can just do some rearranging, and then we have our equation. All right. So here is the solution. So by the time we differentiate this with respect to weight, we have 1. So what's it called? We apply the chain rule. So the summation, and we have this. So why am I not having plus here? You remember, if I differentiate this with respect, if I differentiate P with respect to weight, is 0. All right. So instead of plus, change P here, we're going to have plus 0. All right. So and we're only left with this. So that is the proof. Any questions so far?
If I go through them and I come up with any question, I will communicate
All
through the
right.
thing.
All right. So and also I can also refer you to the material to study, so you can study the material properly. I think
Okay.
you have the textbooks with you.
Yeah.
Yeah.
Textbook
So you can
uploaded.
use Havenia or the Mascole. So find them there. So definitely, so here is another exercise. All right, another equation. So show that. So here's another example. Show that these equations will give us zero. Hmm. So you have to show that the weight effect plus this price and this is a price effect. This is weight effect in its matrix form. So you have to show that if this equation is going to lead to the elastic formula, which are this. All right. So you can practice that on your own. So should we do it together?
Time permits.
I will send the solution subsequently. Time will not permit me to do all of that.
Okay. No problem.
Yeah. So here is another section of this class. So another section is that where our Warashia demand function to satisfy the weak axiom. Remember the weak axiom? Our old friend has resurfaced again.
Yes.
Yeah.
Yes.
So whenever we have something like this, so we want to show that the demand function also satisfy the weak axiom of reveal preference. So how do I show this? So how do I show that I satisfy Wickersham of reveal preference? So we already know what Wickersham means of reveal preference, all right? So this is saying that if we are having the price and the weight, all right? So for this case now, we are going to have two different prices. Let's say X1 and X2. So, or we're having this X and X prime, all right? So P, two prices. Price changes from being P to P prime and the weight changes from W to W prime, all right? So, so when we have something like this, so it's saying that the weak axiom is being satisfied if this condition holds. The price and the weight is. So when you multiply your price, that is the initial price of a particular commodity, to a new price or to a new commodity, all right, the price gives us a weight that we can afford. All right. Then, uh, then if it is not homogeneous, all right, that means the new price is not the same thing as the old, or the new commodity at this new price is not the same thing as this old commodity at this price. Then we can conclude that the new price and this old commodity is affordable, is greater than zero. All right, this is what the weak axiom of reveal is saying. It's like I'm having two prices, price one, price two. I'm having two commodity, commodity one, commodity two. I'm having weight, weight one and weight two. You understand? So that is what we're having here. So if this condition is not satisfied at the new goods, all right, this is the new goods at these prices. So the product of the new goods and this old price exceed what I have, the money we have or the weights we have at present, definitely then this condition should hold. The goods should be affordable at the other price. So that is what the weak axiom is saying. Whenever this condition, that means the new price is not the same thing as the old price, is not homogeneous. So this is how to represent things that are not homogeneous. So that is what the Wickham of reveal preference is saying. So in order to show this example, all right, so I'll give us this as an exercise, all right? So please play with this and submit it on this date. So when you solve this, you want to show, so review your Wickham, all right? So if you look at that properly, so if you look at that Wickham we did in the last class properly, you'll be able to solve this exercise, all right? So you can submit it through my email, all right? So, but let me quickly solve this exercise for this example for us. It said A three. Why do I like three economy like this? A three economy. All right. I remember the last example was three economy. Also, this one to three economy. All right. So a three goods commodity. All right. Consider the budgets. We are giving some budget sets. All right. So the budget set are of this price P1, P2, and P3, and the weight is this. The weight is 8, and the other weight we have it in this form. Okay, we're having one weight is the same for all the three budgets. So now let me quickly show you the solution to this before we end our class. Is my screen visible? Not yet.
Not yet.
All right, thank you. Yeah, I think it is now. Yeah, yeah, here's the question. So to solve this, let's verify the weak axiom of review preference of the choice of this. All right, so these are the three goods that we are given. All right, so these are the goods that we have, goods 1, goods 2, goods 3. So let us also look at the prices. So you know the prices are given also. So let's say these are the prices and the weights. All right, so we have this price P1, P2, and P3, and this is the weight for everything. All right. So now all we just need to do is to play with the Warasa law. Remember the Warasa law. So we need to check for each of them. All right. So the Warasa law says that P dot X is equal to W. So remember the Warasa law says P dot X is equal to W, right? Yeah, so that is the method we are utilizing here. So now here is our P. So we have P1 and we have X1. So we multiply them together. 1 times 2 or 2 times 1. Here we have 2 times 1, 2 times 2. So you sum everything together. This is like P1, X1, P2, X2. You understand? So we are using each of the coordinates to multiply the prices. So that is equals to the weight. So if you look at the left hand side, we have here to be 8, same thing as the weight. Here we have P dot X is the same thing as the weight that was given to us. You understand? So here is 8, here is 8. So what can we conclude from here? Tell us our conclusion.
Homogeneity.
Yes, it's homogeneous. So we can say that there is no reveal preference. All right. So P dot X is the same thing as our weight. So there is no reveal preference in that order. So that we also check for P2. We've done for P1. So we also check for P2 and see if we can achieve that from P2. So for P2, let's find our. So also perform we also perform the same thing for P2. So P2 is like, so you can verify that. So you have 2 times 2. All right. All right. So use it to multiply x2. So and that gives us what? 6. Then for the other one, P2 and x3. So you have uh, the same thing. That gives us 2 times 1, 2 times 2, 4, 2 times 1. Yeah, that gives us 8. So When looking at this now, you discover that these two, one is revealed, one is the same thing as our weight, but the other. So one of this item is revealed compared to the other. Understand? So we can conclude that since uh, they are not the same, all right? So since P2x2 is less than P2x3, so you can say that. That means these two are not the same. You can say that it is revealed. So x3 is revealed preferred to x2. So also we can also check for the last one. All right, so we can also check for the s3. So this is just straightforward. All right. So for the x3, it follows the same order. So P1x1, P3x1, P3. If you do the same thing, we have 9. So you discover that these two, they are the same. The weights are the same, and no choice is revealed here. So it is, in this state, we can say it is indifference. We can call it an indifference situation. So since we are having indifferences here between the choice of x2 and x3, so no one is revealed. Then we can conclude that this relation satisfy this relation can conclude that it violates transitivity, and also that means it does not satisfy the rational preference. Take remember what rational preference says. It must be complete, and it must be what? It must be transitive. So we are unable to differentiate between x2 and x3 here. Also, in one case, we are able to differentiate between them, and the other case, so there is no consistent behavior in this analysis. So we say that it violates the transitivity law. It is complete though, it is complete, but it violates transitivity. So in that regard, it does not satisfy. So we've seen our essence is to show review preferences, all right. But the other question that was associated to the question was to check uh, this if it violates transitivity. Yeah, that was the main question. Check if it violates transitivity or if it satisfies the weak axiom of the review preference. So that is it for today. Let me bring down my screen. Any question?
Now help us to upload it into
All right. Yeah. All right. Do that immediately. Any other question? So please do the assignments that I have here. All right. So in next class, so this is the assignment. We want to show that when you are given this certain preference, all right. So we are giving some goods one, goods two, all right, and these are the price and their quantity. You understand? So all you just need to do is just to check if this behavior is consistent. So check if it contradicts the weak axiom. All right. So and check. So before doing that, you must find your this quantity price. You know, this price is missing. So you have to find it using the Wallace law to find it. All right. So it's very simple. So you do this alongside with the other equation that we have. So this other proof. Yeah. So if you can do both of them together, where is that proof? Yeah. Yeah, this proof. So you can also do it alongside with this proof and see what we make out of it. But in the next class, hopefully, I'll bring the correction before we proceed. So that is all for today.
All right, thank you.
You're welcome. Please don't forget to fill the attendance link. I don't know if it's in this chat box.
I'm doing it.